thank you so much for those of you who came out tonight to come hear about climate change in the evening and this sort of rainy day. So you've probably been staring at this visualization a little bit now, and the reason that I like to show this off the bat is that it's showing you emissions of a sort of a simulation of emissions of carbon dioxide and carbon monoxide. And it's kind of a visual representation of the interface between humans and the atmosphere. So we're actively emitting carbon dioxide and aerosols and carbon monoxide coming from the burning of forests into the atmosphere, and it's getting swirled around. And as we'll see, the CO2 is going to be impacting our climate system in a very real way. In fact, it's already doing so. So what I'd like to do today is I want to talk about climate change, but I would like to use geology, actually, our record of ancient climate change, to give you some perspective of where we might be headed into the future, and also to explain the basics of why we know that higher CO2 will warm the planet and change the environments that we're familiar with. So whether we like it or not, we're headed as humanity down this path towards a high CO2 future. We're putting CO2 in the atmosphere, and we're walking down this future path to a world of unknowns, to the unknown of future climate change. But we know very clearly, we're very cognizant of the fact that CO2 has been rising steadily throughout the industrial era. So how do we know that? Well, we've been monitoring it. We've actually been directly measuring the CO2 rise in the atmosphere for a little over half a century now. For example, monitoring the levels of CO2 on the top of Mauna Loa Volcano in Hawaii. From that long-term monitoring experiment, we can actually see this steady rise in atmospheric CO2 since the 1960s, when we first started actively measuring the concentration of CO2 in the atmosphere. And so here you can see we start in 1960 at about 300 parts per million, and now this is updated as of April of this year. We have just exceeded 415 ppm for the first time in human history. So we've actually seen a 100 ppm rise about in CO2 since actually the mid-20th century. On top of this, you'll see that zigzag pattern. So what that is just the seasonal cycle as the northern hemisphere spring greens up and all the plants take down the CO2. But you can see that zigzag stays the same. What is different here is that long-term rise. So if we want to get even more context for this, we can actually go back a little bit farther, deeper into the industrial period, if we turn to the record of CO2 preserved in ice, in ancient ice. So scientists go to, in some cases, very dangerous places to recover these cores of ice that are accumulating, for example, on Antarctica. And if they cut up this ice into slices, and if you look very closely at a slice of ice, you'll see that it's full of bubbles. And so these are bubbles of ancient atmosphere that's actually trapped into the ice core at the time that the ice formed. And they're this little time capsule. So we can actually go in as scientists and measure the amount of CO2 in those bubbles, and we are measuring ancient CO2 in the atmosphere, which is super cool. And so by doing this, we can overlap with the record from Mauna Loa and go back farther in time. And now we can go back to the 1700s, and we can put this rise in a little more context. So here is the data from Mauna Loa Volcano I just showed you. And now you can't see the seasonal cycle anymore because I'm averaging on a yearly basis. And then the ice cores, they overlap with it, and they take us back to the pre-industrial time. And they tell us that the pre-industrial level of CO2 was around 280. So now we're at 410, 415, but we started at 280, right? So now we have this complete picture of the industrial rise in CO2. So there's an industrial rise in CO2. So the question then is, how do we know this is industrial? In other words, how do we know that this is us? Perhaps there's some kind of, geological event that's putting CO2 in the atmosphere. But in fact, we can definitively rule that out for several reasons. And we can tie this steep rise directly to fossil fuel emissions. And I'll show you a couple ways that scientists have done that. So the first way is actually just simple accounting. All right? We know how much coal, oil, gas we have burned. We can add it up. We can also account for things like land use change. So, deforestation, which also adds some CO2 into the atmosphere. we add up all these pieces and we get a rise in CO2 emissions. So this is just simple accounting. If you burn carbon, it has to go somewhere and it's going to go into the atmosphere. The second, though, is actually chemistry. So it turns out that CO2 in the atmosphere that's coming from fossil fuels, so oil and gas and coal, has a very unique flavor, if you will, fingerprint of ancient dead trees. So which ancient dead trees and algae are what fossil fuels are. Things that died millions of years ago, got turned into rock, now we're burning it for energy, and it has a very unique flavor, fingerprint, that tells you, oh, it's definitely fossil fuels, it's not a volcano. So it's really cool if you measure this fingerprint, which is actually the isotopes of carbon, and so we can measure this in CO2, we can measure it alongside. This is the same CO2 record I just showed you, just a thicker line. And here's the fingerprint. We can measure this in the ice core CO2 and in CO2 today in the atmosphere. And it kicks up just alongside the CO2, 1-to-1, just telling us that this rise in CO2 is definitely from fossil fuels, not from a volcano or some other strange source of CO2. It's definitely us, right? It's definitely us. So why should we care about these are the people who are coming into Aspen in a few weeks. Why should we care about a little bit of CO2 in the atmosphere, right? Why should we care? Well, it's a little more CO2. We went from 280 to 400. What's the big deal, right? So why is that a lot? What does that mean? Okay, so the problem is we know that CO2 heats things up. Why do we know that? Physics. We've known this for a long time in science, going back to the early 1800s when Joseph Fourier, who's a mathematician amongst other things, was the first to propose the idea of a greenhouse effect on planet Earth. And it had to do with the fact that he recognized that gases in the atmosphere interact with energy on planet Earth in a very unique way. And so it turns out gas molecules, stealing from Stephen Archer from the University of Chicago, they vibrate, much like a piano string, they vibrate with only a certain frequency. So a piano string has a certain note because of its length and it only vibrates at that frequency. It's the same for gases in the atmosphere. They will only vibrate at a ringing frequency. So when we're talking about CO2, it interacts with certain frequencies of energy. And what do I mean about frequencies of energy? I'm referring to the spectrum of energy that we know from physics, the so-called electromagnetic spectrum. So a tiny bit of science here, but the electromagnetic spectrum is something we encounter every day, right? So we know that we go to the doctor and we get an X-ray and we have these very high frequency. By high frequency, I mean it's going up and down really fast in time. And that can go through our body and image our bones. On the flip side, when we listen to the radio, we've got this extremely low, slow frequency of energy that we broadcast on the radio waves. And the visible part of the electromagnetic spectrum is what we see. That's what our eyes are designed to detect. Now, the part of the spectrum that is most relevant for climate change is this one, the infrared. The infrared is a little bit lower frequency than the visible light, and we can't see the infrared. Unless you have this app on your phone, in which case you can see the infrared. So if you put this app on your phone, the FLIR app or whatever, you can actually then shoot it at a person, at a coffee cup, and this coffee cup is radiating infrared energy, which is heat, okay, simply put. So it turns out CO2, this is its key frequency. It likes to vibrate with the infrared. When it encounters infrared energy, it stretches, it bends, it does somersaults, which I'm not going to do. Okay, so the molecule is responding to this energy. It's taking in, absorbing it, and then re-emitting it back out, which is what you're seeing in that little graphic right there. Okay, so the infrared is where CO2 is active, the heat part of the electromagnetic spectrum, right? So let's go back to how this affects the Earth system. Okay, so pretty much all of the energy on Earth is coming from the sun. Sun comes in, heats up our planet. And so the planet is heating up like the coffee cup, right? So it's going to emit infrared energy back out to space, just like the coffee cup, right? So if you're standing here, you would see it glow with your app. Now, if we had no atmosphere, all right, then the Earth would actually be a pretty chilly place. It would have a mean temperature of 0. That would be a chilly place, like planet Hoth. So Fortunately, we do have an atmosphere. You know, we do need some heat-trapping gases, otherwise it wouldn't be a nice place to live. So we have an atmosphere which has CO2 in it. And CO2, remember, it vibrates with the infrared. So what happens is once you have an atmosphere with CO2 and other greenhouse gases, they trap the infrared radiation and absorb it and re-emit it back down to Earth, warm our planet a little bit more, and we move up to a much more comfortable 58 Fahrenheit degrees is our global temperature. So that's where we are now, roughly speaking, okay? Now, but there's too much of a good thing, right? There's always too much of a good thing. A little bit of CO2 is a good thing, too much of a good thing, maybe not so much. If we double, oh, sorry, now I hit the wrong button, I'll go through. If we double the amount of CO2 in the atmosphere, right, then we get a stronger absorption of the infrared, right? So now we've got more molecules, they're absorbing more, they're re-emitting it, and the planet gets even hotter, and then we move up to a temperature that's maybe starting to get a little bit uncomfortable for life as we know it. So this is it. You want to explain to your friends how global warming works? There you go, right? More CO2, it absorbs heat, infrared, more you have, the hotter it gets, and therein lies the problem. Because it turns out that even with the amount of CO2 rise that we've experienced, which is 200 ppm or so, well, not quite, but we're, yeah, getting there, we've already seen temperatures rise in response, just as we expect from the physics. So this is a record of global temperatures since the late 1800s, and you can see that it's risen by about 2 degrees Fahrenheit. And so you can see a lot of warming in particular since the 1960s. We've really seen that strong increase. Remember, that's also when we see the CO2 starting to ramp up too in the late 20th century. So temperature is following CO2, and it's rising just as we expect from physics. And so what does this do? You might think 2 degrees Fahrenheit, it's really not that much, and this is the global average, of course. In some places it will warm more, in some places it's warmed less. It's the global average, but we are already seeing the effects of this 2 degrees warming with our own eyes, right? Might not see them in your backyard, maybe you do here in Aspen when you look at the snowpack in the winter, but I'll show you some pictures of where it's obvious that this is really happening. So this is Carroll Glacier in Alaska. A photo in 1906, you see the toe of the glacier there out onto this bay, and this is 2004. You can't really even see the end of the glacier, and this is already 15 years old, so I don't know what the photo will look like today, but a huge amount of mountain glacier retreat, one of the most visible evidence that we have of climate change happening and already changing our cryosphere. If you live in Miami Beach, you might find yourself walking to work in water on a sunny day. So the water that's here, it's not here because there's a storm, it's here because it's high tide. So why is high tide flooding Miami Beach? Because sea level rise, it's already happening. If you live right at the coast, it doesn't take much to start flooding your streets. So Miami Beach has already had to spend a lot of money mitigating what they call sunny day flooding or nuisance flooding because of climate change. And finally, California. So I'm from California. We saw a very extreme drought in 2015. There's a lot of news about it, and it affected other parts of the American West as well. And it's just a visual, loss of water in this extreme drought. And then scientists have shown that this drought is actually the worst drought that's happened in 1,000 years. And they've done that using tree rings. And it's exceptional. And it's exceptional not just because it didn't rain that much this year, it's because the temperature is warm. And warm temperatures means you evaporate more water. So you make droughts worse. It's not just the low precip, it's also the high temperatures that are exacerbating drought. So we're seeing this start to happen all over the place with only the rise in CO2 and only 2 degrees Fahrenheit global. So it just tells you the climate system is pretty sensitive to the amount of CO2 that's up there in the atmosphere. So when we head forward into the future, $1 million question, what's going to happen? Do we expect the weather to get more extreme? Which areas will get wet? Which areas will get dry? How much warming do we expect in my home city? So many questions that climate scientists are tasked with trying to predict this very difficult task. But one way that we can inform the future is actually to look back into the past. Much like the history of societies and people informs us about socioeconomic, political issues today, the history of climate that's in the Earth's past can tell us about where we're headed in the future. And the reason is if we just try to understand climate change by looking at the 20th century, for the time when we had thermometers, it's like trying to understand a game you've never seen by just watching a few plays. So if you're from Europe and you just watch an American football game for like 2 minutes, you're going to be like, first of all, this is a ridiculous sport, but secondly, what is going on? Okay, so the analogy is the same. If we only study climate change in the 20th century, we're not really understanding what the Earth system is capable of. And in fact, where we're going is not like the 20th century. So we need to go back in time further beyond the instrumental record, and we need to tap into the so-called paleoclimate archives of climate change. So in paleoclimatology, we use natural archives that encode in their biology and chemistry the history of past climate change. And some of these archives may be familiar to you. For example, tree rings, which change the width of their ring in response to temperature and precipitation. Ice cores we already talked about as an archive of actual ancient atmosphere, which is really powerful. We also have things like stalagmites in caves, which have this sort of layer growth, corals in the sea, which also grow in annual layers, and sediment cores, finally, which I'll talk about a bit today. So just returning back to the ice cores for a second, I showed you the ice core record going back to the 1700s. But in fact, we have collected ice cores going back almost 1 million years now. And for all that time, we can measure the ancient atmosphere. And this is what those measurements look like. So on the x-axis is time in hundreds of thousands of years. And in the y-axis, the concentration of 2 key greenhouse gases, CO2, and also methane. And what you can see is there's these zigzagging up and down. These are the ice ages, but this is where we are now. So you can see that this 400 ppm level is something that we've never seen in the last million years. And we know that because we can directly measure ancient atmosphere and ice. That's a pretty powerful perspective to have. Okay. Now, let's say we want to go back further than this, though. Unfortunately, this is as far back as the ice core records go. But fortunately, we have other archives of ancient climate change. One of them is sediment cores that we take from the deep sea. So there's an international consortium of scientists that get together, that work together to go out on large ships and collect long sedimentary records of climate change that can go back now for millions of years. So really getting the big perspective on where we've been in the past. There's a special boat. This is the JOIDES Resolution, and it has a modified oil rig in the middle. In the middle of the boat is a hole, and it's called the moon pool. And they drop down this giant piston down into the pool, all the way down into the bottom of the ocean, and then, just like a straw, sink down, get the mud, put your finger on it. Of course, it's a mechanical finger. Pull it back up. But it sounds easy, but we're talking about thousands and thousands of feet of water depth, so it's quite an operation. You need a very large boat. You need a very large winch, and a lot of it. Pull up these sediments. Here's what they look like. They're muddy, for sure. And then you can split them and open them up and take samples. So the sediments accumulate, like the rings of a tree through time, layers and layers accumulating through time. And we're going to go in and then sample at discrete time intervals and try and measure biological indicators, geological and geochemical indicators of climate change. And there's a lot of stuff in that mud. It may not look very interesting when you see it. It's mud. Who cares? But on the microscopic level in particular, there's a lot of fun stuff in there. You can measure microfossils, little mini fossils like coccolithophores, foraminifera. We'll talk about those in a second. Dinos. You can even measure pollen from land if it blows out to sea. You can actually measure things that you can't see, like fossils on the molecular level, or different isotopes, stable and radiogenic, or even the physical properties of the sediments themselves. So there's a huge toolbox to measure in these sediments to get information about climate. The tool I want to talk about today is indeed these foraminifera. And so this is a beautiful picture of one of these guys. And so what are these guys? They're actually protists, and this particular species lives in the upper ocean and has these beautiful feathers that it uses to catch its prey and eat. And so it's actually predatory. Why are they so cool? We find them in ocean sediments all over the world, and they're also very persistent in geologic time. So you can go into the ocean sediments and get out these the shell of the foraminifera, which is made of chalk, calcium carbonate. And these things, they're about the size of a pinhead, so you can kind of see them in person, but mostly, obviously, we look at them under the microscope, but about the size of a pinhead. They come in all sorts of shapes and sizes, and some very beautiful spirals. And they encode in their chemistry, actually, some very important information about the Earth's climate in the past. So I'll show you some data that comes from analyzing these guys in old sediment cores. So the first thing I want to show you is that actually we can use the chemistry of the forams to get at CO2 beyond the ice core record, which is extremely powerful. So this is the ice core record again in this sort of turquoise color. And now time is in millions of years. So you can see it takes us back about 1 million years. Those are all the zigzags I'm talking about. Here's the 400 ppm boundary where we are at today. And then back further in time are these measurements based on the foraminifera. And so we're looking at CO2. They're spotty. They're not as continuous as the ice core. But we see that we have to go quite a bit farther back in time to get to the point where these dots start to go above the 400 ppm. In short, the forams tell us that the last time CO2 was as high as it is now is 2.5 million years ago. So that's a long time ago, even for geologists. So it just shows you how unusual our current situation is. So what's happening 2.5 million years ago, the last time CO2 was above 400 ppm? What did it look like then? What was the climate like? Let's take a look. Welcome to the Pliocene. So this is a model simulation, actually by a person who's here. And I should mention the last slide. Several of these slides feature data compiled by people in this room. So as an aside, you should go talk to them after this talk, because there's amazing work of the people in this room that enables us to look back into the past. So this is a model simulation of the Pliocene. And you can see that almost everywhere is warmer under this higher 400 ppm. And just to put some numbers on it, in the higher latitudes, we actually see something like 7 degrees Fahrenheit warmer. And in the mid-latitudes where we are now in Aspen, just offshore of California, we're seeing something like 3 degrees, maybe 4 degrees Fahrenheit warmer. So keep in mind, so far we've experienced about 2 degrees global average. This is more than that, but the current climate change we're experiencing hasn't actually ran out, right? We still have some climate change baked into the system, which we'll talk about. So warmer in the high latitudes especially. And in fact, we had almost no Greenland ice sheet. So the Greenland ice sheet was gone, mostly gone. So that's pretty amazing, right? 400 ppm, that's where we are now, no Greenland. It's gone. We know that, geology. It's easy to tell that some of it was gone. Also, we hadn't even evolved yet. So this is Lucy. And Lucy shows up around 2 million years ago, but she's our ancient ancestor. Remember, Homo sapiens, we only evolved 200,000 years ago, order of magnitude later. Ultimately, we are an ice age species. We've never experienced a climate like the Pliocene. We're adapted to go hunt mammoths and stuff. So anyway, the point is the Pliocene is a climate that humans don't know, that we didn't even evolve in. It's something that's that foreign to us, 400 ppm. What if we want to go back farther? Lucky for us, as I said, the foraminifera, they're found really far back into the geologic record. And so now I'm showing the other thing that we can infer from them beyond CO2 is temperature. So we can actually use the geochemistry to get temperature. So here's a temperature curve, global temperature. And now we're going back. You see the timescales are getting increasingly longer and longer. We're going back the entire Cenozoic era, 65 million years ago. So here's where the dinosaurs died. And this is what's happened since then. And so you can see here's the Pliocene. We just talked about it right there. Last time, 400 ppm. Around this time is when the Antarctic ice sheet forms. Before that, no Antarctic ice sheet, no Greenland ice sheets, no ice sheets. And check this out. At some point, around 55 million years ago, we had a global temperature of around 80 Fahrenheit, which is pretty steamy. Here's today's temperature for a reference. Okay, so this is a big change. Now, what's driving this change? Well, lo and behold, probably CO2. So we can see that when we go back to that time, 50 million years ago, when we have really hot temperatures, we also have very high CO2 at that time in the order of 1,000 ppm in the atmosphere. Here's where we are today for reference. So now we're talking about a climate that has much more CO2 than we have today. So the Pliocene is here and it's similar. Now we're talking about something that's way more. However, as I'll show you at the end, this is not outside the possibility of where we could be at 2100 if we just continue to burn all of the fossil fuels. So if we do nothing, we can actually get to 1,000 ppm. So that's why we're going to take a look at this climate, which we call a greenhouse climate, because it's so warm. Okay. All right. So what's a greenhouse climate like? Let's look at the geology. The geology and the paleontology tells us something about what life was like in a greenhouse climate. First of all, there are big, big snakes. So in case you're thinking this is tropical paradise, you probably don't want to be walking in a rainforest and come across Titanoboa. So this is a normal boa constrictor vertebrate from today. This is the vertebrate of Titanoboa, which was hanging out in the Paleocene and maybe the early Eocene. It's pretty scary. Well, you know, why was there giant snakes? So snakes are cold-blooded. They can't regulate their body temperature. You know, so one idea is that Titanoboa really liked the kind of steamy climate of the Eocene, so snakes were able to get real big. What else? So this is what the world looked like in the Eocene, this greenhouse climate time. 56 to 34 million years ago, CO2 is around 1,000 ppm, no ice sheets, climate was steamy. And you can see sea levels quite a bit higher too. The continents are a little different. So we haven't yet completely, India is still smashing into Asia, but you can see it's pretty similar. You can still make out the continents, so pretty similar. This is an artist's rendition of an environment in the Eocene showing some mammals and some crocodiles hanging out, sort of rainforest place. And the crocodiles, actually, we find these guys all the way up into the Arctic Circle, which is pretty crazy considering that crocodiles, that today at least, really prefer to live at around 85 degrees. So, you know, if we're finding these in the Arctic, then you can't get too much cooler than this for them to be happy. So it really tells you that, man, that Arctic must have been nothing like the Arctic that we see today. And what about the Antarctic? Well, actually, if we go to the Antarctic, we actually find evidence of palm trees growing on the coast of Antarctica. Basically, it's like a Caribbean beach. Okay, not quite, but you know. Palm trees, baobab trees, which are a tropical species from Africa. In a sediment core, we can recover pollen from both of these guys, perfectly preserved. That tells us, no kidding, there were palm trees growing on Antarctica. So that also really drives home that these high latitude places that today are pretty chilly, and not a lot of people live up there and enjoy it, we're very, very toasty in the greenhouse climate. And in fact, what we call this sort of distribution of temperatures in a greenhouse climate, we call it a Moreequable climate. And by that, we mean that two things. First of all, that we think the seasonal range in these warm climates was smaller, so that the winters would have been much warmer. So the summer-winter difference in the continents was reduced. And we also think that from the geology, we can have a look at temperatures across different latitudes. And so today in the ocean, our tropical oceans are around 80 degrees Fahrenheit. But if we go, of course, up to the Arctic and Antarctic, we see that they're near freezing, right? That's sea ice, so it's freezing. Now, we know from geochemistry indicators and also fossils that the tropics were warmer during the Eocene, and they're now getting up to sort of hot tub temperatures. But the real amazing thing is a difference in the Arctic and Antarctic. So again, thinking about the crocodiles, you know, 70 degrees C up there. So that's a really big change. So people talk about the poles warming more in the future, and that's actually exactly what we see in the past, is the poles warm more than the tropics. Yeah. Okay. Now, you might think that a warm climate would be pretty stable. There's not ice sheets, so perhaps they're not rapidly melting and causing problems. But actually, we've discovered that a warm climate is not actually a stable climate. What we see when we zoom in on the geologic record is these incredibly rapid climate changes superimposed on the greenhouse warmth. So here I'm showing you that global temperature reconstruction again, but this time I've smoothed it less because I want to call your attention to this little blip right here, which doesn't look like much, but if we zoom in, we can see that, in fact, global temperature spiked around 55 million years ago by about 5 degrees Fahrenheit. And in geologic timescales, it's very rapid. This was a 100,000-year event. So very rapid in comparison to the long-term change that we're seeing here. This is a rapid global warming event that we call the Paleocene-Eocene thermal maximum. It's a bit of a mouthful, admittedly. So this is very interesting because this is very fast global warming event. We can learn from it because, in fact, we're experiencing a fast global warming event right now. So it's considered an interesting thing to study. So I just want to give you an overview of what we think happened during this PETM event. So basically, we have, first of all, some kind of burp of CO2. Boom. OK. And then we see at the same time from our indicators of temperature, boom, spike in global temperature, 5 degrees C. I just showed you that. And then this is even more interesting. We actually see a dramatic drop in deep sea ocean chalk or calcium carbonate that tells us that during this event there was massive ocean acidification. All right. So CO2, high temperatures, ocean acidification. 3 things, they happen together. And you don't actually need fancy chemistry to tell you this. If you just look at the sedimentary record of the PETM, we can actually visually see this event. So before the event, this is a deep sea sediment core taken from the South Atlantic, and it records the PETM essentially visually. The change in that deep sea calcium carbonate is something you can see. So before the event is on the left side here. So here we have this sort of muddy, light sort of, chalky but still brown ooze, and it's full of the ocean chalk, which by the way is made of foraminifera mostly. And then, boom, the PETM hits, and we see that sharp line, right? So we have the sense of an abrupt event, sharp boundary, and we move from sort of whitish to red, dark color. And the dark color is this red clay. All of the calcium carbonate is gone. And so that tells us that this place in the ocean experienced acidification, a very large amount of it. And so CO2 is an acid, actually. So when we put it in the ocean, we expect the ocean pH to drop, and we can actually see that right here in the sediments. It's pretty amazing. And in fact, we see this in sediments all over the world across the PETM, so it's not just in one place. After that, we continue just to deposit the red clay as the oceans are too acidic to actually support the deposition of chalk. But finally, the system does recover. It takes 100,000 years for the climate system to bounce back from this event. So 100,000 years to bounce back from this rapid global warming. Okay, so what do I mean by where did it come from? Where did the CO2 come from? Obviously, there weren't humans emitting fossil fuels at this time, so it had to come from a natural source. And there's quite a few theories about that. It could have come from volcanoes. It could have come from permafrost melting out in Antarctica, maybe. Or maybe it was the release of these so-called methane clathrates, which are also called fire ice, because there's methane inside the ice, so you can actually light this thing on fire. These things are, underneath sediments offshore continental slopes, and they form there under relatively low temperatures and high pressures. But if the ocean warms, it can release them, and so they could have possibly contributed to the CO2 burp as well. Scientists are still debating which one of these, or maybe all of them, contributed to the PETM. So this rapid warming event is quite useful as we look in the future because we talk about ocean acidification, and we're actually seeing it in real time happening now back 55 million years ago. This said, it is still a much slower event than what we're currently doing. So this graph compares the rate of change of temperature during the PETM, the onset of the PETM, to the rate of change of temperature if we continue to emit at our modern rate. So our best estimates from the PETM is, even though it appears like just that sharp boundary, we think it still might have taken 10,000 or maybe 20,000 years to ramp up, with an emission rates of about 2 petagrams of carbon a year. However, today we are emitting order of magnitude faster, so 25 petagrams of carbon a year. Where we are today, right, I said we only have 2 Fahrenheit, but if we continue to emit at that rate, we're gonna shoot up pretty scary. So basically, the PETM is one of our best analogs for rapid global warming, but honestly, it's not quite as rapid as what humans are capable of doing, right, by artificially burning all the fossil fuels. So, all right, so let's return to the present day and the future. So I hope that the geologic contest gave you some idea that when you put CO2 into the atmosphere, stuff happens. The earth warms. We've seen it time and time again in the geologic record. We know that global warming is real. We know that it's caused by us. And we also know that it could be bad. You know, that we as humans, as an ice age species, are not particularly well adapted to a warm climate, but neither are the other living things on planet Earth today, right? They all evolved in the ice ages. But I don't want to end on a note like that. So I want to talk about how there's still choices, okay? We can still determine where we end up. It's not too late. There is hope. And it's very important that we make choices quickly to determine what will our future climate trajectory be. So let's just look at some panels from the IPCC report. Short story, where we end up depends on how much we emit, period. More carbon, more warming, more stuff. But we have a choice. How much are we going to emit? So I talked about these two warm climates today, the Pliocene, the last time we're at 400, and the Eocene, the greenhouse climate. So this is showing you future emission scenarios to 2100. It's just showing you the parts per million of CO2 in the atmosphere, and this is showing you the amount of temperature that would be caused by these different amounts. So here we have 400 to 500 ppm, and I'm calling that the Pliocene situation, because if we can stabilize in this zone, then we're going to see a warmer climate, but it's not the Eocene situation where, like I said, we could reach to 1,000 ppm if we just do business as usual, right? 1,000 ppm is what we know we had in the Eocene. We didn't have any ice left, so that's not great, right? So Pliocene-Eocene situation leaves us with a very different CO2 and a very different temperature rise. Here we're around 3 degrees maybe, but here we're starting to get to 5 or 6 degrees, and things could really get shook up. Similarly, if we look at the projected change in temperature between those a little more specifically, we can see that in the Pliocene situation, which essentially is aggressive mitigation of CO2 emissions, would stabilize global temperature just slightly warmer than today. Business as usual, another matter entirely. And this also matters for ocean acidification. So, the difference between the Pliocene situation and the Eocene situation is pretty clear. If we can cut carbon emissions, we can actually stabilize the pH of the oceans and perhaps save some of our coral reefs. But if we allow emissions to continue at their maximum, we're talking about PETM levels of acidification. So there's a choice. It's very clear, Pliocene or Eocene, right? So obviously, it'd be very difficult to stay in the Pleistocene without actually technologies to pull CO2 out of the atmosphere and put it back down. But still, just looking back at geology, there's very big differences between these two climate states. So to quote Sherman Rowland, who won the Nobel Prize in Chemistry, our point of view, coming as climate scientists and coming to you, is what is the point of developing a science well enough to make these predictions if in the end, all we do is stand around and wait for them to come true? So we put it to you to make the decisions, to make the political decisions, to change our energy usage so that we can avoid really disruptive climate change. Okay, so with that I'll say thanks, and I think we have some time for questions.